Fourpole Creek Watershed by Richie Combs. This is the location of the second part of Fourpole Creek that I'm using for this presentation. It is still at Ritter Park, and it is right next to the tennis courts here at the bottom using Google Maps. I have the about accurate location of where the marker says that my location is at. This is a second view showing the roadside version of my same location. The yellow line indicates a rough estimate of where the stream that I had used is currently situated at. This is a Google Earth image showing the same location, showing from where the top of the stream where I had done research at to the endpoint of the stream, going from upstream to downstream, as well as the approximate length of the stream itself. The length is listed on the left in case the image was too small to see. The purpose of this PowerPoint is to determine two protocols for my stream, and to do so requires a number of variables, starting with this, the width of the stream being approximately 3.5 feet wide, while the height of the stream is approximately 4 feet tall. This is an extreme point where up ahead you can see, to the right of the image you can see a flag, and to the far back to where the person is situated, over there to the right is a small orange flag. We had listed a amount of flags along the stream in order to determine our work area. We have the tops of the walls here, which show the various sort of red clay vegetation growth and roots that are coming out, as well as some images of the small shallowness of the stream and the rock count. This is a second view of the stream taken from the same location but showing from atop the bank. The flag is situated right there, and it is much easier to see just how wide it is and tall it is. This is further down the stream at a different portion where we can see still having a high coverage from where the top of the bank to the bedrock currently is situated at, with a tree here that is that has half of its earth being removed underneath it while still hanging on to the bank side. This is, according to the Google Maps and Google Earth data, a visualization of the approximate length of the stream being about 493 feet, or more accurately 492.64, I believe, as shown in the previous images, which roughly estimates to about 150 meters. This is a second view of the length, taken from the endpoint of the stream going up further. The line is a rough estimate of where the beginning point would be, as is currently being obstructed by the tree coverage. This is an example of the rock count for the pebble count. For the most part, there were a large number of large size rocks in here, while the most of it can consist of much smaller counts, such as sand or silt in some cases, to just being some few pebbles. This is from the same part of the stream, just taken from looking downstream instead of upstream. Here you are able to see some parts of pollution, being a small broken piece of bottle in the center and lower right portions of the yellow square. We have much larger rocks being shown here, being deposited where the stream is currently not flowing, and the much more uniform sized rocks being within the stream itself. Here is a close-up of the rock collection that we had. It's much easier to see the effects of the pollution being in this picture, although it is slightly distorted. For the most part, there was a large amount of larger rocks and smaller rocks being placed within there. That most of the large rocks were placed in the areas where the water was not reaching that side, and so the larger rocks were left to be deposited there. For the first assessment of the stream requires the NRCS equation requirements, as we had gone through the bankful measurements using the dimensions of length, width, and height of stream. Sinuosity uses stream length, the valley slope, length, channel slope, which was found using Google Earth. The entrenchment ratio uses flood-prone width, which uses bankful depth, which is the height. Dominant channel soils uses bed materials and materials of left and right bank. Riparian vegetation uses what kind of growth is available, how much is covered, the height of it, and bankful height. Bank slope uses slopes of size and length, and the pebble count need to be estimated from the pictures that were presented earlier. This is the first of 3 set pictures for the NRCS equation. For here we have Fourpole Creek in Cabell County. The bankful measurements. The valley slope had been estimated using a elevation chart that had been made in Google Earth, as well as the valley length of it and the channel slope, with sinuosity and sinuosity being measured for the length and slopes. The entrenchment ratio is the flood-prone length is water level at ×2 maximum depth with the bankful depth, and assuming so, the flood-prone width being 8, and the entrenchment ratio being converted from there, which is the flood-prone width divided by bankful width, which gives us a measurement of 2.28, which is a slight entrenchment ratio. The dominant channel soils, assuming from the pictures where you could determine the height of the stream, assuming that they have slight brown to red color tinting. So I was assuming soil and clay, and the left bank containing roots that are poking through, while the right side of the bank did not have as much. This is the second set of the NRCS pictures. where we have riparian vegetation, which is mostly grass, and then grass shrubs being on the right bank, the total amount of area that it covers, and a total height of the roots being somewhat minimal, and the bank slope being determined for roughly about 7 feet, give or take, and using the information primarily from the entrenchment ratio, it is assumed to be a type stream E. This is the estimated pebble count using what I had found in the pictures, using a rough estimate of 50 pebbles being used in order to determine about how approximately how many of these would be available if given the chance to thoroughly go through them. Using the entrenchment ratio of greater than 2.2, we were able to first determine what area it would be in for single threaded channels, being either a E or C, and then determining that the width to depth ratio is much smaller, being lesser than 12. We were able to work it down and move into a E type channel for our stream type. For the BEHI equation requirements, it uses the ratio of bank height to bank full height, the ratio of root depth to bank height, root density in percent, bank angle in degrees, and surface protection in. This is the first of the BEHI field form, using a rough estimate of the bank height being greater than 2.8, the root depth being approximately 50 to 89, the root density being 30 to 54, the surface protection being roughly about 80 to 100 for the vegetation growth. This is the second portion of it, containing the latitude and longitude of the location, the surface protection, which was stated previously, then the bank angle of the stream. The first assumption of the Behe score needed to be readjusted once I had noticed the sections for material adjustment, where we had found boulders, cobbles, gravel, and sand, which had affected the information by adjusting it plus 5 points. And then the stratification adjustment, where the bed layers would have several scores of different materials making up the layers, and assuming that they are various earth, rock, and clay layers that led to multiple layers, and the assumption of a total score of 41, which is a very high BHI rating. This is the math I had done in order to determine the amount shown. To the second information is currently incorrect, as it had not yet included the information needed for the material adjustment and stratification adjustment, though the math should come out to 41.